Feels like a Friday or something, but Friday actually will be a complete work day. We'll get through this content together. Um, it's 9.4, measuring dispersion, spread, standard deviation. So you may have seen this in a high school class or any type of statistics class if you've ever taken it. So its calculations are pretty straightforward. Um, so we'll go through those. You can also use a graphing calculator. We'll do it. I'll show you how to do that, put in the data. But we're also, again, dealing with the probability. So we're tying in random variables, which gives it a slightly different feel, but we'll be we'll be connecting back to what we did in 9.3 under expected value. So it's kind of important that you didn't do 9.3, maybe go back and do that because we're going to use some of it. Although we will do it, and there was a couple interesting methods, or at least one that the PowerPoint had. I said, oh, this is a much better way to do it. So I'll show that for one of the examples um, that that wasn't done in the previous. Okay, let's go ahead and get started. And then again, Friday will be sort of an open day to get caught up on a few things. We might go start off with a few questions from the test review, just to kind of get you going on those. Whatever we do, I'll record that session. And then as we move into individual work, we sort of stop recording after that. But we'll try to get a few of those in there. Okay. So we talked Monday about central tendency, the middle. Where is the middle of the data, right? So we had two ways of doing that. One was the mean, where we just calculated it, add everything together, add all the data, divide by however many pieces of data. So if there's 10 pieces, we divide it by 10. If there's a million pieces, we divide it by a million. So whatever that. So add it together, divide by however many there are. So we did that. What we're going to look at today is a different aspect of data, and that's how spread out it is. So once we find the center, then we could have two sets of data that have the same center point, the same middle, but they could look very differently. So here's an example. You get a grade on your recent midterm. We just had test number 2. Say it was 68%. Class A average was 72. That might sound, hey, I did pretty well. I'm pretty close to the average, right? And in one instance, that might be a very good score because, let's see, at 68, oops, I didn't want to do that. Just a moment. Get my writing tools back. There we go. 68 would be just under 70, so that would be about here. So you'd be there, and that's pretty close. But the data might look different also. It could look like this, and here's your score. A lot of people scored higher, so you're maybe below. Again, I'm not saying a lot of times we're in education, we're always comparing to someone else. Maybe we should compare more to ourselves. Maybe 68 was good for us. So, but that's, we rank people. How are you doing and compare to everyone else? So, but this is where spread of the data makes a difference. We both have the same average of 72, and we're 68 is still close to that, but again, it just makes a difference of here 72 is about here, and there's a lot of scores that were above it. So that's just how it works. So what we're talking about is that, again, the data could have a similar sort of midpoint, which, like this stuff, I would, just eyeballing it, it looks like both of these have about a midpoint somewhere around here. So they're grouped around the same middle, but their spread is different. That's what we're measuring today. So when we calculate these numbers, the bigger the number, the bigger the spread. It's hard to really understand what those numbers mean. We'll try to give meaning to them, but we come up with a number, and it's just kind of indicating whether a big spread or a small variance or a large variance. Okay. So what we're doing is we're looking for the variation, all of these calculations, we're first going to have to calculate the middle. And for these calculations, what we're doing, we're going to focus on the mean, adding together and divided by however many there are. So we'll be pulling back that calculation again. And again, remember with the mean, there were two types of means. There was a population mean and a sample mean. And so the same thing happens. There's a population variance and a sample variance. And there's a slight difference that's, as we'll see, I don't know, it's really not important because if you have a population, you're going to have a lot. But let me show you that difference first, and I'll let you know why it's really not a big deal, but they make a big deal out of it. Okay, so the variance, what we're going to do, I skipped a couple slides, so if you go to the full one that talks about what they tried that didn't work, I said, let's just talk about what works. So what this is you're taking each data point and you're subtracting the mean. So you're finding whether it's above or below the mean, right? It would be negative if it's below the mean. It'll be positive if it's above the mean, but that value will be how far from the mean each piece of data is. So we're doing it with x1, with x2, x3, and so forth, all the way to the last piece of data. We're subtracting it. Now, the reason we square it is because if you just try to get the average of the variation, you would always get 0, because about the way we do the calculation, that middle means that not necessarily half is above and below, but that arithmetically, the top and bottom, because the bottom will all be negative, the top will all be positive, they'll be the same values, and when you find that average, you always get 0. So it's not very helpful. So what they do, and again, you could read about they could try the absolute value. Well, that causes some problems. Anyway, what we're going to do is we're going to square each of these numbers, and when you square a number, what happens to it? If it's negative, it becomes positive. If it's positive, it stays positive. So now all the numbers are positive, and if we add them together, we get a value. And what we're going to do is divide by however many pieces there are. So what we're getting is a sort of like the average distance from the mean, right? Because you're squaring it, but it's the average distance squared, right? So this gives us an average distance squared, which what we do then is we unsquare it, right? Because that was a manipulation to make it positive. If we unsquare it, taking a square root, then we get something that's meaningful, okay? But you'll see they call this the variance, which is sigma squared. There is a place in statistics, in advanced statistics, where you'll actually look at the variance itself. We calculate the variance only so that we could take that next step and get the standard deviation. We will use, and most statistics will use just the standard deviation. I always had a problem with this. Why didn't you even talk about the variance? Why not just take the square root at the beginning and just, because standard deviation is what we're going to use, right? But then when you get to more advanced statistics, then they'll talk about variance itself, the sigma squared. So I guess that's what they're trying to set you up for. But for us, we just need to get this number here, which is, click standard deviation. Okay. Deviation is how far away. It's sort of standardizing how far away the average piece of data is. Does that make sense with the calculation? And that's how we would do it. So we're getting, again, sort of the average of the spread. And so this we would call one standard deviation. If we do it with a sample, the calculation is just slightly different because a sample generally is going to be a smaller size, right? Population is everything and usually is very large numbers. But with the sample to make everything work, and again, this is just in the theory and the research, whatever they did, what they end up doing, not dividing by the number, but one less than the number. So if there was 10 pieces of data, we would divide by 9. And it just makes things work. We'll just put it that way because they don't have any other big reason. Now, the thing is if you, again, for those of you who are going to take more statistics, you'll see this thing called degrees of freedom, and it's how many pieces of data we have. Once we get to about 30 pieces of data, it doesn't, the difference between these two is so small that we don't even really care. And so if you've got more than 30 pieces of data, oftentimes you will be able to use the population. Less than 30, you definitely want to use this sample variation. So I just say, why don't we just always use the sample variation? Because if I get over 30, this is going to be so close to this, I can't tell the difference. So to me, that's what I would do. Okay. Mostly we're going to be doing this, but be careful. Even if there's only 10 pieces of data, that might be a population, then we're supposed to go use that one. And so there could be some differences. Your calculator will calculate both. And when I get to that step, I'll do a calculation. I'll show you on the TI-84 how you can tell the difference. And it will give you one is, I think one is S, right? One is, this is variance. It's not standard deviation yet. We have to take the square root. So now it's standard deviation, sample standard deviation. So it's S and sigma. And that's how you'll be able to tell the difference. One is a population standard deviation, one is a sample. So as you go through the questions, just kind of be mindful, are they asking for a sample or are they telling us this is a population? Because that may give us a slight difference. Yes. Exactly. That's the only thing. So it's still getting sort of the average, but if you've got a small number, subtracting the one gets us closer to what's makes all the rest of the theory work that we're not going to get into. But always, and I'm not a statistics specialist, certainly. I've done it, I taught it, but I did not get a degree in statistics. And I've worked with people who have, and I can tell that they know all this stuff like that. And they know why it is. And I talked to them, I said, oh, okay, it's good to know. Things I didn't think were important, well, to them, it's important because, that's what they do. So variance and standard deviation. So a lot of what we're going to do, that's basically what we're going to do is that calculation, we'll see it. But we're also going to do it for random variables. And again, it changes slightly there. So we'll go through that. So let's do some examples. Sample variance of the scores 1, 2, 3, 4, 5 is the sum of the squares of the differences between the scores and the mean. So again, the first thing we need to do is calculate the mean. And how do we calculate the mean? Well, we add them all together. And I think that's going to give us 16, 10, 15. So that gives us 15. There's 5 items, but they told us it's a sample. So do we divide by 5? No. Oh, wait. For the mean, we do. Okay, yeah, mean is, okay, sorry. That's what I see, it just confuses us, right? So for the mean, we divide by 5, and that gives us a mean of 3. Okay, so this is what did we use for mean? This is X bar, because it's a sample. Okay, so we calculated that. So once we got that, then we take each piece of data, we subtract the mean from it, and we're going to square it. And you'll see if you have a lot of these, this gets very tedious, right? But again, we'll enter them into a calculator, have them do it for us. But just to understand what's going on, take each piece of data, subtract the mean, square it. Each piece of data, subtract the mean, square it. Each piece of data, subtract the mean, square it. Each piece of data, the last piece, subtract the mean, square it. And then we're going to divide it all by n minus 1. So I'm going to write it as 5 minus 1. Okay, so I've entered all that just to remind us because it is a sample. And we gave us this. And so what we're getting is samples is S squared, which is the variance. It's not really what we want, but it gets us to there, and then we'll take the square root. So let's just kind of do this. 1 minus 3 is negative 2. Negative 2 squared is 4. So these numbers are not too bad. 2 minus 3 is negative 1. Negative 1 squared is 1. I like this one. 3 minus 3 is 0. 0 squared is 0. So we don't have to even write it, but we will. 4 minus 3 is positive 1. And we square it and we get positive 1. 5 minus 3 is positive 2. And we square it and we get positive 4. And we're going to divide that all by 4. And part of this is you'll see, did you see exactly how, when you look at these numbers, if we had left those numbers negative, the bottom would have subtracted from the top, we would have got 0. And that's why we can't, we want to kind of get that spread, but it just didn't work. So we do a mathematical manipulation. That's why we're squaring it. And then we're going to take the square root to get back to there. So that's 4 plus 1 is 5. 5, so that's a 10/4, which is 5/2, which is 2.5. Yeah, 2.5. So about 2.5 is the average here, and that kind of makes sort of sense. Did I get that right? Yeah, it doesn't feel quite, a little bit, not quite 3, but now 3 would be the median, but the arithmetic average is 2.5. Oh, wait, but we're not done yet, right? That's, um, uh, sorry. See, I keep going back. The average is 3. The mean is 3. Okay, so we're right around here. What number did we get? We got s squared is 2.5. But what we want is we want s, so we're going to take the square root of both sides. And so s is equal to, what's the square root of 2.5? Someone could, 1.58, with a lot of other repeating numbers, right? Or decimals, yeah, 1.58 to 2 decimal places. So what this is, let me just focus myself, right? Average is 3, and then the spread is we're about 1.58 above, 1.58 below. So it's kind of, if we've got symmetry, which this is kind of assuming symmetry. And if we look at that, if we go about 1.58, we're about here and about here. So that's kind of getting how spread things are. If the number was bigger, like if we were at 0 and 6 instead of 1 and 5, our standard deviation would have been a little bit bigger, so because it's a little more spread out. If the numbers were more packed, like 2, 2, 3, 4, 4, same number of numbers, we would be more compact. Our standard deviation would be smaller. Okay, so that's kind of what the standard deviation is giving us. Does that make sense? How much above, how much below on average. Okay. We're using this as like a real world application. Mm-hmm. So what is the variance that presents scores and then the standard deviation? I can't answer your question about variance, just being honest. I really don't, because we don't use it. It's more advanced statistics. They'll use that variance to do something. But the standard deviation is what we're going to focus on. Standard deviation is what's the average deviation from that middle. It typically is used when we're comparing 2 data sets, right? If we just got 1 data set, a lot of times all we need is a mean, but it can help us. It says how spread out was that. If it's a smaller number, it just gives us this idea of spread. And that's why typically it's mostly when we're going to have 2 pieces of data, we're comparing it to something else, which data is more spread out, because they might both have the same mean, that middle, but we could then kind of get a picture of what the data itself looks like. Or, if I'm a farmer and I've got averages on size of my potatoes or whatever I grow, so let's say potato size, and I would also have I know they're not all at the mean. Some are big, some are small, but maybe one year I notice I got a lot of smaller and a lot of big, there's more variation or something. So I'm wondering what's going on. Maybe the fertilizer isn't getting evenly distributed or something like that. So that's where we could use it. Let's see. Had that. I wrote over the top of everything, so I can actually go ahead and delete this. That was just to help us get through it, and you get it nice here. They get the square root. Same thing we got, 1.58, right? And then, actually, they got the variance. But notice they didn't calculate this for us. They just said it's 3. They figured we'd have to do it. That's why I wanted to work it on our own. You always have to find that, if you're just working with the data. You have to find the middle first, the mean first. Okay, let's look up. The bottom stuff's not supposed to be there. I don't know why. Well, it is. So here's just another example. We've got incomes in thousands of dollars. So this is our data. To calculate the mean and the sample deviation, or standard deviation, and this is a sample. like to get this out of the way, but as you can see, they're subtracting 40 from each, so they get, you know, the mean is going to be 40, so you just add them together. 50 plus 40 plus 60 plus 20 plus 90 plus 10 plus 30 plus 20. And then we divide it by 1, 2, 3, 4, 5, 6, 7, 8. So that's kind of why I want you to see these is, you know, it's easy to kind of get confused, but we always divide by the total number when we're getting the mean. And yeah, they put it there. Do that. Add them together. 320 divided by 8 is 40. The next step to getting the variance, again, it's not something we use, but we use the square root of it because we square it. So we subtract the mean from each piece of data. This 1/7 is just the denominator is 8 minus 1, right? That's the n minus 1. 8 minus 1 is 7. So they just multiply by 1/7. Do all of this. This is 4,800 divided by 7, which gives us a standard deviation of 26.2. And now this is where we're actually going to use it, and it'll kind of give us a feel for what it means. So what did we have? We had our mean was 40, right? That's the middle. And if we add 26.2 and we subtract 26.2, so actually that's not a good way to do it. Let's, well, actually I could leave that one. We could, and we could take, well, we'll do a 26.2 minus 40. Because it's in statistics is standard, if we're below the mean, we usually use a negative number, that, you know, because those numbers are going to be the same. One's above, one's below. One standard deviation above to one standard deviation below. And what we're going to see, so if you take 40 minus, or 26.2 minus 40, what do we get? We get negative 13.8. Is that right? -40 minus 26.2. Did I get that right? Okay. 40 plus 26. I can do this a little easier. It's going to be 66.2. So what that's saying, if we were to put these in order, which I did, I was pretty smart last night. So I put them in order so that we can kind of visualize this. 40 is the, oh no, I didn't. I missed. I was trying to put it in order, but I wasn't as smart as I thought I was. 40 should be here, right? The 50 should go there. Okay, so we'll call this 40, and we'll call this 50. Okay, so 40 is the mean. And what we did is if we go one standard deviation above, we'd be at 66.2, which would be about here. And if we went one standard deviation below, we'd be at 13.3, which would be about here. And so there are 1, 2, 3, 4, 5, 6 pieces of data that are in that range, from one standard deviation below, above to one standard deviation below. Does that kind of make sense? So that's what we call what this is. One standard deviation above. This would be one standard deviation below, and we have 6 out of 8 pieces of data, which, if we do that, is about 70-something%. I'll click on here because it's in here somewhere. So this is what we're doing. Again, we could leave it as positive, but just when you're doing statistics, you'll usually, the number below is negative. 13.8 to 66.2. So that's the range of data we're looking at. It's 6/8. Yeah, I thought it was about 75%. So 6 out of 8 pieces of data are in that range. It's about 75% of the data is within one standard deviation. That's what that number tells us. Okay, at about, and there's a special rule. We're going to see another one. So it's around somewhere around 70, 75%. It's not a hard and fast rule, but generally that's what's going to happen, about 70-ish percent. We're actually, the number we want to get in our mind is 68% if it's a normal and everything else. If there's a lot of data, it'll be 68% is what we use. And we'll see that in a moment. How about 2 standard deviations, right? Let's see, what did I get? For 2 standard deviations, we would add 26.2 times 2, which is 50. So we take 26.2, multiply it times 2, and get like 52.4. And so we'd go 52.4 above, 52.4 below. And in this case, that would put us, if you add 40, we're at 90 something, right? So we're over here. If you subtract that from 40, you're into the negative number. So you're here. You've got all the data included, 100%. All of the scores. And the theory says if 2 standard deviations, generally you have about 95%, give or take. Okay. In this case, because it's a small bit of data, it's possible we could have it all, but it's also generally we want to think it's about 95% of the data is within 2 standard deviations. And again, that standard deviation is dependent upon the data. So as the data change, so so the more spread you get, the bigger that number is, right? The mean, it doesn't affect the mean. We're using that mean, but the more spread out the data is, the bigger the standard deviation is. And so it doesn't matter how the data changes. This is a general rule that tends to work. Okay, so here's our empirical rule, and if you look at the other PowerPoint, you'll see something called Chebyshev's, which works if it's not bell-shaped. We're not using it in the homework. We're not using it here. Usually, you don't use that in statistics unless you're getting some really advanced stuff. Most of our first level statistics that we use is considering what's called a normal curve, the bell-shaped distribution. So that's what I took that stuff out, and let's just focus on the bell shape because that's what we're going to use, right? But also let you know that there's other types of distributions and there's other theory. But again, if you get into statistics as a major, or if that's what you're going to be your focus, you'll get to those. Okay, so we're going to focus on that. If it's not symmetric, we're not going to talk about that or this, but those would have different formulas and different stuff that goes on. But if it is bell-shaped, this is what happens. We find the empirical rule states, look this up, that whether it's a sample or a population, if we're 1 below to 1 above, 68% is what we will use. So there'll be some questions about this on the homework. You want to remember that 68. Why 68? It just is. A lot of research has been done, and over time, if it's got this shape, this normal distribution, 68% is 1 below to 1 above. And actually, if you use the tables, it's like 68 point something something, but we're just going to use 68. And then what we find, 2 below to 2 above, that spread that you'll get 95% of the data. So this kind of gives us, a picture. And then the last one we go to is over 3 below to 3 above. We don't actually have 100%, but we'd have 99.7. So that's most of the data. There still could be a few pieces out there at the very ends, but if we've got this, when you see it talking about the empirical rule, we're assuming it's got this bell-shaped. Again, not always a good stuff, and generally if we've got the stuff we're studying, that's going to happen, especially as we get larger numbers of data. Okay, so empirical rule is just this sort of spread. And I think we got a picture. Yes, we do. These will be the ones. Yeah, we're still recording. Okay, we're back. These are the 2 pictures you might want to just kind of remember. So 1 below, 1 above to 1 below, 68%. 2 below to 2 above, 95%. It's a good picture to have. And we sometimes could use this. We're not, again, this is not going to get into heavy statistics, but we will be using this in the normal curve when we get to 9.5. That's about the end of our data. So we're not going to take this too deep. Okay. So we'll deal with that. So those things we want to know, we'll get through the homework. Now we're going to, nothing new, we're going to take this concept and apply it. What if we had a random variable? So we've got some randomness going on. We're going to assign random variables to our data. How does this all work? So part of it works in a similar way um, that we were doing on Monday. We were calculating the expected value. So we're going to need to do that because that's basically the same thing as the mean, right? The expected value of a random variable is the central tendency. So we're going to need to calculate that expected value, and we'll do a couple examples where we will do that. So that'll help bring back to memory that. And then once we've got that, we calculate the standard deviation of, actually, what they call the variance, we take its square root, and that gives us a standard deviation of a random variable. So similar concept, but again, sort of one level of abstraction on it. And again, they say if n is large, the sample and population variances are essentially the same. And that's what I was saying, because the only difference is population, you divide by n, sample, you divide by n minus 1. But once it's about 30, and if you can look at tables of this, once you get to 30, the two numbers are always about so close that you have to go out to like 8 decimal places before you see any differences. So they're good enough. So what we concentrate on, a lot of this part, we're looking at population variance, because why? If we're talking about a random variable, we have a lot of trials. N is supposed to be large for random variables to make sense, right? Probability, you need large numbers. You can't do probability of 2 events because there's too much variance. Okay, so we've got larger numbers. So we'll from this part, we're going to be talking about population. And again, what we're looking at is the variance, or how far each piece of data is from that expected value. We're going to square it, and then we're going to take its square root after we add them all together. So the average value can be predicted using this. This is the expected value. Remember, it's the each variable subtracting the mean squared. So remember, this mu is what we used for the expected value of the random variable. And so we'll make the following definitions. So the variance of x, so this is, and again, x is that random variable. We calculate really in the same means, except what we do is we take the data value minus the mean, which is the expected value, we square it, and then we multiply it by the probability. Okay, so that's this random variables always have a probability of happening, and they might not all be the same, right? Might not be equally likely, but that's what's going to happen. That's the addition to this formula. So it's really the same thing we did. We take each piece of data, or in this case, the data is the random variable, which could be like rolling a dice would be a 1, 2, 3, 4, 5, 6. Whatever that random variable is, we subtract the average value, expected value, we square it. So that's this first part. And with data, we were done. I mean, then we'd add them all together. But with random variables, we have this additional step, multiply by its probability of happening. Okay, so it's sort of this gives us a weighted value. Because if it's got a higher probability, it's going to happen more often. So it's got more weight in this equation. Okay, and we do that for each piece. Again, take the random variable value, whatever it is, subtract the mean, we square it so that it's all positive, otherwise it would all cancel out, and then we multiply it by its probability of happening. And we do that for all of them. We can do a shortcut formula thing that just take the value of them. That's what that is. And then at the end, once we've got that value, right, we take its square root so that we get what we can use, which is its standard deviation. And again, for me, I went through years. Why are we always calculating the variance? Why do they even talk about it if we never use it? And then 40 years later, I took a statistics class that used it, and I go, oh, okay, now I understand. So sometimes you just got to go far enough, and then you start to see where it's used. Whether you go there or not, at least know that there is some kind of reason for it. But So far, we good? So that all we're adding, same kind of calculation we did, but now we got to multiply by that probability. And there's kind of a neat little feature that that I saw here. We're going to go through this one, and then we'll look at their answer afterwards. But what they did, I don't know why I didn't think of this in the past. So they're giving us a distribution, and it hasn't. They tell us it has an expected value of 2. Now we could also calculate that, right? Because the expected value, to calculate that expected value, we take x times the probability of x, right? So we take -1 times 0.3, and we're going to get -0.3. We take 0.5 times 2, which gives us 1. We take, and maybe I'll put a line here, right? We're multiplying. We take 3 times 0.1, that's 0.3. And we take 10 times 0.1, moves the decimal over 1, which is 1. Wait a minute, did I get this right? 2 times 0.5. Yeah, I did. And then when we add these together, here's a -0.3, here's a positive 0.3, so those are going to cancel, right? I've got 1 plus 1. Oh, it's 2. So they didn't do that for us, but that's what we're going to have to do probably in the homework. And I just want you to see we can do this, and we're going to keep building off of this now with the next step. But are we okay? That's sort of the average, right? That's how we calculate the average with a random variable. The random variable times its probability. Boom. Now, hopefully I remember everything we're supposed to do. The next step is we want to calculate each x value minus that average, right? Let's go back a step, right? We want to do this part. We're going to do this, and then we're going to multiply by that, and then we're going to add them together. Okay, so then that's going to give us our variance. Okay, so we want to take the random variable minus the mean. Oops, going the wrong way. There we are. Okay, and we're going to want to, well, I'll do it in 2 steps. So I'm going to do this first, and then we'll take it, and then we'll square it, just so we can see the steps, and then we'll add them together over here. So the x is -1. I want to subtract -1 minus 2, right? So I'll actually write that out because, and that gives us -3, right? This one is 2. I'm going to take 2 minus 2. I like that number. That gives us 0. This is 3. I'm going to take 3 minus 2, and that gives us 1. And then I'm going to take 10 minus 2, and that gives us 8. And that I just want you to see that's what's going on inside. Now, again, we could probably use a calculator for a lot of this, but this is, and then we want to square each of these because you could kind of see, well, we don't get 0, but we don't, we do get some canceling out here, don't we? Yeah. We want to square each of these, so that gives us 9. -3 squared is 9. 0. 1 squared is 1. 8 squared is 64. So that's that. And again, that's this first part of the calculation. Now we want to multiply each of those by the probability of that random variable happening. Okay, so I want to take this 9 times 0.3. So I want to, well, let me cheat a little bit. I forgot. So I just want to make sure I'm on the right track. Close your eyes and now you can look. So what we're doing. Yeah, exactly. And then we're going to add them all together. Okay, good. So what are we doing? We're taking the 9 times the 0.3. 9 times 0.3 is going to be 2.7. 9 times 3 is 27 with the decimal place move, gives us 2.7. This one's easy, because 0 times anything is going to be 0, right? This one I take 1 times 0.1, so I get a 0.1. And then I take 64 times 0.1, I get a 6.4. I add all these together. That's 2, 8, 9.1, 9.2. Good. And that's when my cheating, I saw that it was 9.2. So this is a great way to learn. We couldn't look up. The back of the book has all the answers. So we'd always pick a question that had the answer. You look at the back of the book and you always work backwards. That's how I learned a lot. So this is what we just did, this formula thing. And we got 9.2. But what is that? Is that the standard deviation? No, that is our variance. That is sigma squared is 9.2. How are we going to get the standard deviation, which is just sigma? We're going to take the square root of 9.2, and that's going to give us 3 point something, right? 3 point. Someone help me with that one. It's on the next page, but we'll just do it here. 3.0 something maybe, or maybe 3.178. Am I getting any closer? 3.033. Okay. I thought there might have been a O in there, but I know the square root of 3 is 9, or the square root of 9 is 3. So, okay, and that's our standard deviation. So on average, so what this is telling us, the expected value of our random variable is 2 with a standard deviation of 3. So that means we could be 3 above to 3 below. We'll see about 68% of our data, right? If we go 2 standard deviations above, 2 standard deviation would be about 6, right? 3.0, 6.06 to be exact. If we go 6 above to 6 below, we should have about 95% of our data. Okay, that's what that's going to tell us. Let's go to the, but what I want you to see here is this method. Yeah, oh, there it is. I should just hit, we got 3.03. What I'm going to show you is they do it here. So this was the page that sort of taught me. I said, oh, that's kind of a cool way to go through it. I just, so you might want to set up a template like this, because that's where I was struggling. I couldn't remember. I think, all I got to do is this. But we'll go ahead and do this kind of on our own, knowing that we've got this template. We might have to cheat a little bit to make sure we're on track. But same thing here, right? This is our data. Looks similar to stuff that was there. But again, it's a random variable, and so each has a probability of happening. So that variance and standard deviation for the following probability distribution. Again, we don't ever really use the variance except to get the standard deviation. That's sort of the ultimate goal. But in the process of getting it, we're going to have to find the expected value, the average, the mean. Then we're going to have to find the variance. We take its square root, and then we finally get its standard deviation. Okay, so again, we'll try this. How are we doing on time? Let me see. I want to see what's left. Oh, that's going too slow. Let me just let you say that this is here. This is basically what we just did, right? This 2 is 0.2 times 10. So we're multiplying. And then once we have, we add all these together, and that gives us our average value, our expected value, right? The mean. Notice we subtract the mean from the piece of data. So 10 minus 30 is negative 20. That's what's going on here. We square each piece. We multiply each piece by its probability, and then we add them together. And then we take its square root. Okay. Now notice we're not dividing by however many pieces of data is, because we don't really know how much data is there. These are random variables with weighting, so that those probabilities are working as the division part of how many there are. Okay, so we kind of get away from that part. And so that gives us a standard deviation. So for this particular one, we can say the average is about 30. We would expect that to happen. But 68% of the time, we would expect that our number to be 15 above or 15 below. And 30 above to 30 below, so between 0 and 60, we would expect to see about 95% of our data. Okay, so it's all there. We'll go with that. Now, if we have the special case, it's so simple. This one's always thrown me. If we have binomial, and what's a binomial? Success or failure. So there's really just two, in this case, thinking of two random variables. We either succeed or we fail. So if we know one, remember, we know the probability of one, the other is one minus that. So, and that was that simple, the simple formula is simply that we take the number times p. However many trials we do, and this time we bring into it the number of trials times the probability of a success, that gives us our average value. So this is a very simple calculation with Bernoulli or binomials. And then the formula for the standard deviations, even more simple. It's simply n times p times q. So it's kind of like the expected value, but then we also have to multiply by the probability of a failure. And that gives us the variation, but the variation is not the standard deviation. What do we need to do to get the standard deviation? Take the square root and we're done. So these are very simple calculations, but you just have to remember, again, they'll try to fool you, or maybe, in the way they sit, you have to, the hard part is reading and saying, oh, this is binomial, success or failure. If you ever get a problem that's saying it says this much percent for success or something, success, failure, this is how we think of things, and look at the calculation. I could do these all day, right? It's just multiply the numbers and maybe take a square root. And remember, Q is 1 minus P, so they don't have to give us Q. And oftentimes they won't, and you're going, what's Q? Well, it's just 1 minus P. So as long as they give us the probability of a success or the probability of failure, we can get the other one. And then we just need to know how many trials there were, and boom, we just multiply n times P. There's the average, n times P times Q, square root of that. There's our standard deviation. So we'll do a quick one here because there's a couple in there. So probability of success, they've got 20 trials. That's our n, right? Trials is n. 70, what's the standard deviation? We don't actually even have to calculate the mean if we don't want to, because we don't need to use it. Standard deviation directly, and we could use this, I guess, well, or maybe we use sample, whatever. Standard deviation is going to be the square root of n times p times q, which we were told n is 20, p is 0.7, so q must be 0.3. And remember, I just took 1 minus 0.7. There we go. Simple. Can't do it in my head, but somebody could do it for me, or I could just click the button and it'll tell us 2.5. Much simpler, much simpler. Just the only thing we have to do is ensure that we have a binomial or a Bernoulli trials. But usually the way they set it up, that's what they're telling us, right? And again, if we're doing Bernoulli trials, usually they're large enough. And we could, well, actually they tell us if n times p is greater than 10 and n times q, the probability of success, are also, if both of those are greater than 10, then we can use the empirical rule of 68%. We've got enough stuff going on, but it depends on the probability. So 50-50 is different. So binomials look different depending upon the difference between p and q. But we could do a quick check on this, and then we say, okay, if we take n times p and we get bigger than 10, then we could say it's pretty much like a normal distribution. Or n times q is bigger than 10. Both of them actually have to be. Okay. Another example, and this is like a homework problem, so we'll just do this one and we'll close it out. So we got a 40% chance that something's going to happen, 25 hits per day, right? So how do we calculate what are the expected value and standard deviation? Expected value is simply going to be n times p, which in this case is going to be 25 times 0.4. Again, I'll just, I think I didn't, yeah, I took all that out. So that's our expected value. Expected value is that. What would be the standard deviation? Standard deviation is, let's see, what's 25 times 0.4? Anyone got that? Quickly. How much? 10. I should have known that, but okay, 10. So that's our average. Standard deviation is going to be the square root of n times p times q. So that's going to be 25 times 0.4 times 0.6, square root of that. Oh, I got a calculator right here. Stop being so lazy, little girl, and just plug it in. Times 0.4 times 0.6, and then take, that's 6, and the square root of 6 is 2.44, 2.45 rounded. So we've got 10, and again, remember that rule, if n times p is 10 or bigger, so we're about there. And then we can kind of, what does this say? We could expect to get 2.45 below 10, oh, actually 95%, 95 days out of 100. What we would expect is to take that 10, subtract 2 times that standard deviation, that would be at the lower end, and 10 plus 2 times the standard deviation. So this number goes here, that's the lower end, this is the upper end. So that's going to be about 4 point some, maybe about 5. So it looks like about between 5, that's going to be about 5 and 15. So approximately 95% out of 100 days, I will get between 5 to 15 successful hits. So it's kind of like if I'm running my business, we can do this. Okay, so taking those. Homework's going to be similar. Take that, come back on Friday. If you have any questions, we'll work through things together, or if you just want to come and have a work party, we can do that. Bring some coffee and whatever. Donuts, no, I'm trying to cut off the donuts. Take care, and then we've only really got one more section, right? 9.5 with the other part with it, but we'll put all this together and then we can start reviewing for the final. Actually, it is. We were assigned this, usually there's some other classroom, but we were assigned, our final will be in this room, but it'll be Thursday night at 7:10, which is totally different than what we've been, our schedule, but it's common finals, but we did get the same, this is 174, isn't it? Yes. I'll double check it, but we got the same room. Thank you. Okay, perfect. Good idea. Maybe I'll just enter it now and then you won't have, I'll do that.
Should I send you like a class number?
No, no. Don't even send me anything. I'm going to do it right now.
Oh, okay.
Okay.
Thank you. Final posted on the homepage, like the date and time.
It's on the date and time is on the syllabus. I'll make a statement with the room number now that I've got it as well. So yeah, you too. Hi guys. Yes, shine. Okay. And the difference is they'll tell us somewhere in the question whether if we have the population, it means we got everybody, and usually that's a large number. Sample is going to be usually less than 30, or so they'll tell us it's a sample or it's a population.
So like the questions always tell us.
Yes, they have to let us know. Yes, you're welcome.
Is the final gonna be like kind of like similar to the other exams we've taken, or is it gonna be a little?
It should be about the same. We do get more time, but it's a third test, so I haven't, again, this is my first time teaching it, but it should be, it shouldn't be any longer because we're not going to go back into that other material.
Yeah, that makes sense. Oh, so you don't me to do like the same
One,
things on
yeah,
one and
one or
two?
two. Now, some of the stuff from the two we're applying here, but we
Yeah.
won't have questions like two. We'll have them only like what's in the homework for three. Sure.
I'm having a hard time understanding like this type of problem. I guess.
Okay.
Like,
Okay, the following table shows approximate numbers of schoolgoers in the country, residents attending breakdown by age group, blah, 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 blah. Use the rounded midpoint of the given measurement classes. So they're saying 5 is about the middle, 10.5, okay, to compute the probability distribution. So the probability distribution is just really the relative frequency. So we're going to take 13 divided by, so we need to get the total.
okay.
13 divided by the total will be this probability.
Okay.
13, so this will be the same. This will be 19 divided by the total. 15 divided by, yeah, of these numbers. Okay. And so that will be those probabilities. And then, so that's the harder part. Then to get the expected value, this is not binomial. So then we take the x times that, this times that, and then we add those all together.
Okay.
And that'll give us that.
Okay.
What information is expected by residents enrolled in schools. So in 2000, the average blank was this many years old, because that's what these are actually ages.
Got it.
Right.
Okay. Thank you.
You're welcome.
That makes more sense.
Yeah, that's what I mean. But it's
bit,
yeah, it's kind
hard
of
to
this
visualize it.
abstraction of
Yeah.
what's really going on here, and random variables just